On the evening of June 24, 2026, the northern coast of Venezuela tore open. Within 39 seconds, the region experienced two massive seismic ruptures. An initial magnitude 7.2 foreshock struck first, followed almost instantly by a larger magnitude 7.5 Mainshock. The origin point for both of these earthquakes was located roughly 150 kilometers to the west of Caracas. Yet, despite that vast distance from the epicenter, the most severe structural damage did not occur in a uniform radius. It was highly concentrated in specific coastal developments far down the fault line. Look closely at where the devastation was focused. The structural failures overwhelmingly targeted public housing blocks built under the Gran Misión Vivienda Venezuela, or GMVV program. Entire residential complexes experienced total structural separation, leading to the complete pancaking of roofs and load-bearing walls. This hyper-localized destruction was the result of a specific chain reaction. To understand why these particular buildings fell while others stood, we have to trace the energy back to the mechanics of the fault line itself. Northern Venezuela sits on a complex plate boundary, where the Caribbean plate grinds eastward past the South American plate. This motion is absorbed by interconnected strike-slip faults, primarily the Boconá, San Sebastián, and El Pilar systems, operating on the exact same mechanical principles as California's San Andreas Fault. At 6:04 p.m., the first slip occurred. A magnitude 7.2 foreshock nucleated on an onshore segment of the Boconá system, releasing energy over 23 seconds. Then, the moment release stopped. For 15 seconds, the network was quiet, but the immense pressure transferred laterally to the adjacent San Sebastián Fault. This sudden loading pushed the fault past its failure threshold, triggering the magnitude 7.5 Mainshock exactly 39 seconds later. The precise sequence of these two ruptures set the stage for the disaster. Because the second quake was triggered by the first, the geometry of the slip dictated exactly which direction the devastating energy was about to travel. The Mainshock nucleated just 7 kilometers to the east of the initial foreshock, right along the Yumare Morón coastline. As the fault tore open, the rupture did not spread outward evenly. It propagated rapidly in a single, continuous eastward direction along the coast. Seismologists refer to this dynamic as unilateral rupture directivity. Because the rupture front is moving at roughly the same speed as the seismic waves it generates, the waves pile up ahead of the tear, much like the Doppler effect you hear when a siren speeds toward you. This wave compression takes the scattered high-frequency seismic energy and packs it into a tight, highly amplified directional beam. That focused energy traveled straight down the strike of the fault, pointed directly at the dense population centers of La Guaira and Caracas. The geometry of the rupture concentrated the destructive force into a high-amplitude beam, projecting an amplified pulse of energy far beyond the immediate epicenter and into the capital region. When the directed wave of energy reached the eastern coastal cities, it encountered highly variable geological conditions. The city of Caracas is built squarely on top of a deep, sediment-filled basin. Just to the north, the coastal city of La Guaira rests on soft, loose fluvial sediment fans. This underlying soil composition triggered a phenomenon known as site amplification. When fast-moving seismic waves transition from hard, solid bedrock into soft sedimentary soils, they slow down. To conserve energy, the amplitude of the waves dramatically increases, violently magnifying the ground shaking and prolonging its duration. This chart maps the peak ground acceleration zones across the region. You can see how the contours spike severely over these soft soil locations. The localized shaking demand inside these sediment zones far exceeded the strict parameters laid out in the region's Covenant 1756 building codes. The local geography itself betrayed the cities, catching the energy from a distant epicenter and converting it into a sustained, violent shaking event right beneath their foundations. Which brings us to the Gran Misión Vivienda Venezuela housing complexes, rapidly built starting in 2011 to address a severe housing deficit. To meet extreme production quotas, many complexes were built with systemic engineering flaws, utilizing low-strength concrete and non-ductile structural designs, incapable of flexing under stress. They lacked adequate foundation coupling. Many multi-story buildings were placed on soft slopes without the deep foundation piling required to anchor them to solid bedrock. The intense ground shaking caused severe settlement and ground coupling failures across the soft coastal fills, physically separating structures from the earth meant to support them. In this residential building, you can see the catastrophic result of lacking bedrock support. The foundation failed entirely as the loose soil shifted underneath it. But this raises a critical question. Why did these specific low-rise GMVV buildings suffer total collapse when taller, adjacent structures survived the exact same shaking? The answer is found in soil structure resonance. Every structure has a natural period, the specific rate at which it naturally sways back and forth. Because the GMVV buildings were short and rigid, they had a very short natural period. By fatal coincidence, that period exactly matched the prolonged resonant frequency of the soft alluvial soils they were built on. The buildings and the ground moved in perfect phase with one another. Each seismic wave amplified the structure's sway further and further until the non-ductile concrete shattered and the buildings collapsed. This exact mechanical sequence is not without historical precedent. The 2026 doublet closely mirrors the catastrophic earthquake template of 1812. The 1812 disaster was also a doublet event, and the 2026 rupture occupied the exact same western segment of the plate boundary. To understand the future risk, seismologists use Coulomb static stress transfer modeling to evaluate how this rupture altered pressure. By rupturing the western segment, the 2026 doublet relieved local pressure, transferring a massive load of static stress to the east. That newly loaded, unbroken central offshore strand of the San Sebastián fault now points directly at Caracas. This creates an immediate engineering imperative. Independent, non-destructive structural audits of all remaining GMVV complexes must occur right now to assess their lateral load capacity. The 2026 doublet shifted critical stress onto the segment pointing at the capital. Retrofitting surviving infrastructure is a necessary survival measure before the eastern segment inevitably fails.